Assalamu alaikum wa rahmatullahi wa barakatuh. So this is another important, very important thing. Well, before I do anything, this is the password per one. This is the password per identity, number. And yes, packet switching, we're not going to do it yet because we haven't even studied the chapter. Now look, before I even talk about this question, there is one thing I must mention, and that is these two words, precision and range. Sometimes the word accuracy is also used, AWCURSEY, right? But mostly precision is used in the marking scheme, right? So precision and range. What are these two things? So in all of the previous questions that we have done, for example, this one, right, and this one, in all of these, know one thing. There were different number of bits given to store the mantissa as well as the exponent, right? So the number of bits you use to store the exponent or the number of bits you use to store the mantissa have an impact on the number that is being stored, on the data that is being stored, right? So the only thing that you need to know and the only thing that you need to keep in your head is the fact that precision has to do with mantissa and range has to do with exponent, right? When the number of bits when the number of bits being used, let me say it again just because I want to. When the number of bits being used to store the mantissa increases, then the precision of the number being stored or the precision of the mantissa that is being stored, it is also going to increase. Obviously, if the bits that you're going to use to store the mantissa are going to be less, then the precision is going to be reduced as well. Same is the case with the exponent, right? But the only difference here is the word we're going to use is range. So the more bits you have to store the exponent, the greater range of numbers is available to us that we can store, right? But if we are going to use lesser numbers to store the exponent, then obviously a smaller range of numbers can only be stored, right? If the number of bits for storage increases, then the precision increases as well, right? And if the number of bits for storage decreases, then obviously the precision is going to decrease as well. Now, if I copy this entire thing and I paste it here, I think, yep, this is the exact same thing. The only difference is we use the word range in here. This is it. You know. Now, what actually happens? Another thing that you must understand. Let's say I've got myself a mantissa, right? And that mantissa is 0 1 0 0 1 1 1, right? So how many bits are these? 1 2 3 4 5 6 7, right? So I've got 7 bits. Now my computer system says, hey, I don't have enough, storage. I'm a weak old man, so I cannot give you 7 bits to store a mantis. I do like, come on, So he says, I'm going to, store this in 5 bits. I'm going to store it in 5 bits. So the original mantissa requires at least 7 bits, right? But your computer is old or any kind of, problem it has, it says, I can't store it. I'm sorry. I can only give you 5 bits, right? In that case, let me make that same thing, right? 1, 2, 3, 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Now we've got ourselves 5 boxes. Okay. Now take a look at this. I told you that the mantissa is always to be written from the left to the right, right? It has to be written from the left to the right. So if I start writing this, if I try to fit in this, or if I try to plunge the 7 bits mantissa into only 5 bits, what's going to happen? I'm going to start writing it 0 because this 0 is significant. I cannot just remove this 0, because if I was to write a 1 here, it would mean that our binary number is negative, which isn't the case. So this 0 is something I must write in here. So it's 0 1 0 0 1. And what about the other two zeros? They're lost, right? Now look, these two zeros had what? They had weight, you know, weight. This is a term that we're going to learn more about in another chapter, and that is AI, artificial intelligence. We're going to learn more about it, okay? But for now, every single bit has its own weight, right? Now, for example, if I was to write it here, 1, 2, 4, 8, 16, 32, and then 64. 8 and 16 and 64 may not have any weight. Why? Because when you try to find the binary value, you're not going to add them because there's a 0 under them. But 2 and 1 do have weight, right? 32 have weight, right? 32 has weight. You know why? Because there's a 1 in here. And it is going to play a big part, a big contribution when we're finally going to find the final sum for it, right? Now, before we even try to find the final sum, we know that these two bits are lost. We were only able to write 0, 1, 0, 0, and another 1. What about the last two? So these are called, the bits which have weight are called significant bits are lost, right? So if the exam question asks you what is the impact on the number being stored if the number of bits used for storing the mantissa decreases, you would say the precision decreases. If they talk about the exponent, this you would say that the range decreases. If they talk about increasing the storage, well, then the range would also increase, the precision would also increase. If, let's say, I bought a new computer, I tell him that I need 7 bits. He's like, oh, 7 bits is not even that much of a big problem. You can take 10 from me. He literally said, you know what? You can take 10 or you can take 20. Let's do 10 bits this time. 1, 2, 3, 4, 5, 6, 7, 8. I think that would be enough. So let's start writing this in here. How many bits even are they? 1, 2, 3, 4, 5, 6, 7, 8. 8 are enough, or let's just do 9 and 10 as well, right? So if I start writing it here, it would be 0, 1, 0, 0, 1, 1, 1. And the rest of them are zeros, right? Because, I mean, when you're not left, when you have extra space, you just write zeros in there, right? Now, my main number, whatever I wanted to write, is what? It's same, right? My new number is same. It's not different at all, is it? But if I want to store a larger number, I still can, right? I still can. Or in other words, how much even is it? It's, 32 plus 4 plus 2 plus 1. 32 plus 4 plus 2 plus 1, right? That gives you a 39. In binary numbers, it's 39, right? This is also 39, but if the precision increases, I can also write point, 000 this time. This is way more precise, right? This is way more precise, you know. Or let's say if it wasn't 39, it had some fractional part. If I was to store it in just 5 bits or even 7 bits, it will lose some significant value, right? But now with extra space, I can store more numbers to store, its precision, its accuracy. And the same case is with the exponent, right? Now we learned about two things. How the number of storage being used to store the mantissa or the exponent impacts their precision or range, right? That is the first thing we learned. And the second thing is what happens, if we use, if you don't, use or give the mantissa or the exponent the required number of bits it needs, then what's going to happen? The significant, the weightful bits are going to be lost. This is also called, I forgot the word, nutrification. No, not nutrification. Now let's take a look at the question. And that word I'm talking about is different, okay? I don't know why, but the word kind of just flew over my head. Never mind. So let's just read the question. Now, the numbers are stored in a computer system using binary float point representation with 12 bits for the mantissa, 4 bits for the exponent, and two's complement form for both of the mantissa. You know what this line what this line means? It just means that you've got this 0 0 0 0 blah 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 whatever. How do you know whether this number is a positive binary number or a negative binary number? The least significant bit is going to be 1 if it's negative, it's going to be 0 if it's positive. That's it, right? That's the two's complement form. So you have 12 bits for the mantissa, right? I know my writing is really bad, but never mind. And 12 bits for the exponent. It says outline the effect of changing the number of bits used to store the mantissa to 10 bits. So instead of giving the mantissa 12 bits, we're only going to give it 10 bits. What's going to happen? The precision is going to decrease. So the way I'm going to write it in here is this. Precision for mantissa or number stored in mantissa decreases, right? So the very first thing is the precision of the number stored in mantissa is going to decrease. Why? Because we gave it lesser numbers this time. Now, if we took 2 bits away from the mantissa, then now we have 2 extra bits. We can give those bits to the exponent, right? So now the exponent has 6 bits. You know what? I'm not going to waste my time writing it in here. I'm just going to explain it to you. 6 bits for the exponent, right? So it's 6 bits for the exponent. And yeah, 2 bytes in total. That's not exactly. You know what? This is important in knowing, that the 2 bits we took away from the mantissa are still in our need. We're just going to restrict the mantissa to, 10 bits. So the exponent gets the other 2. Now, if the exponent is going to get more bits, its range is going to increase. So range increases for exponent, right? Or the marking scheme wording for that is, that the number of bits available for the exponent will increase to 6, obviously. This will increase the range of numbers that can be stored, in the exponent, right? So the range increases. You get 1 mark for talking about the precision. You get 1 mark for saying that the remaining 2 bits go for the exponent. So now the exponent has got 6 bits, a mark for this and a mark for talking about the increasing range of the exponent. You've got 3 marks. Done. Now, describe one example of a situation that could cause an overflow to occur and the consequences of such an overflow. Now, an overflow is obviously not something, you shouldn't be familiar with. You should have been familiar with it. If you don't know, it's a simple thing. You've got a glass of water, right? If you're going to pour too much water into it, then what's going to happen? It's going to overflow, right? That's some pretty terrible drawing in here, but I mean, bear with me on that. Same is the case with what happened in here. Let's say you've got 10 bits for storing the mantissa and you multiply 2 large numbers, right? And the product of those 2 large numbers resulted in a number that was way too large. It needed more bits, but you only had 10. It needed 15 bits or 20 bits, but you already had 10. So what happened? Significant bits were lost. This is what happens. Significant bits are lost when an overflow error occurs. That's it. So how you're going to write it in the marking scheme kind of terminology. Now, first you have to write, what situation can cause this multiplication. For 2 large numbers. I'm writing very rough here just so that I can give you, an overview. Now, you know what? It's not like you have to memorize these points individually. It's more about concept, right? One thing leads to the other. So if, you're going to multiply 2 large numbers and obviously, the product of them is going to be outside the range of values, right? It's going to be outside, the number of bits, right? And that is going to lead to the significant bits being lost, right? So I'm just going to write significant bits lost. That is one thing. And before that, the result would be, or product would be outside of range. The range, you don't write you don't have to write it the way I'm writing it. I'm writing it way too short form. Obviously, do elaborate. If you do want to know exactly how it is to be elaborated, then you can go and check the marking scheme. But the main concept has been given here, so you're going to get 3 marks for mentioning this. The situation, and what the situation is going to lead to. So the situation is multiplying two large numbers. You can write something else over here as well. The arithmetic operation that gives you the largest numbers is multiplication. So if you're already going to multiply two large numbers, the product is going to be even more larger, right? And obviously that might be outside the range of values that can be stored. So you got 2 marks for explaining the situation and its consequence, and maybe the consequence of the consequence that is going to grant you 3 marks. Significant bits are going to be lost. That's it. So I think that would be enough for our topicals for floating bit representation. Let's now move on to the next section of computer science. Okay, and that is it for today. Assalamu alaikum wa rahmatullahi wa barakatuh. This went a bit too longer than usual. This was 15 minutes. Okay, assalamu alaikum wa rahmatullahi wa barakatuh.